Welcome back to ECE 501B. Homework number 7 is due a week from Thursday. I just need to change the assignment. If you've already looked at it, apparently it's for my other class. So I better change that and make it for 501B. And the project, I'm going to have to go back and check that to make sure that that's okay. That should be online, and that's due at the end of the first week of December. And it's that particular date because I don't think we're supposed to give you any major anything due during finals week, and finals week begins on that Friday. And our final exam, I believe, is a week and a day from that date of December 7th. I believe it's December 15th, Monday. I don't remember the time, but it's probably later in the day than earlier, if I had to guess. We'll make sure and be aware of that as we get closer to that date. But now, hopefully after class, I will get that assignment changed to be reflective of this course. And again, that's due a week from Thursday on the 20th. Last time we were in an exam, so let's return now to where we left off, which is returning to Chapter 7, and I think that at the very end we simply stated Proposition 7.6, which was an if and only if on t being normal. If we have an operator t that's normal, that's true if and only if the norm of that operator applied to any vector is the same as the adjoint of that operator applied to that same vector. The qualities of norms then mean that the operator is normal. We will then look at showing that an operator produced by taking t dagger t minus t dagger, where t dagger is the adjoint, will show that that's self-adjoint as an operator. Then we will look at a couple of properties on normal operators. One is a relationship between the eigenvalues and eigenvectors of t and the eigenvalues and eigenvectors of the adjoint of t, or t dagger. And we'll see that they share the same eigenvectors. Their eigenvalues are conjugates of one another. That's the relationship. Then we will look at distinct eigenvalues, again for normal operators, and we'll see that if you have distinct eigenvalues, those correspond to orthogonal eigenvectors for a normal operator. Again, that's all under this heading of the operator t being normal. Then we'll get into sort of the big result, which are some spectral theorems, and it actually depends on which space you're working on, which spectral or what the results can be. For complex inner product spaces, t being normal is true if and only if, or that implies that you have an orthonormal basis of eigenvectors. When you have a real inner product space, it's more difficult, or it's more constrained, and there you actually have to have your operator being self-adjoint, not just normal. If your operator is self-adjoint, then you have an orthonormal basis of eigenvectors. Let's now return to Chapter 7, and here's the proposition that we stated at the end of our last period together prior to the exam, and that's Proposition 7.6. Hopefully this is still in your notes, but I thought, you know what, I probably need to restate it. An operator t is normal if and only if the norms are preserved between t and its adjoint. And here is a proof of that particular proposition. t is normal, and here if I sort of do if and only if all the way down, I've proven both directions simultaneously, if that's okay. So here t is normal if and only if. That means that the operator commutes with its adjoint. So we could write that as t dagger t minus t dagger is 0, or t dagger t is equal to t dagger. That's the same thing. If that's true, then that left-hand side is just a 0 operator in a sense. And if we have the 0 operator operating inside an inner product, meaning if we now take t dagger t minus t dagger and apply that to v, that's just the 0 operator applied to v. That's 0. Inner product with v. What's 0 inner product with any v? This is true for all v in our vector space, capital V. What's that equal to? If this now is 0, which we just said it is for t being normal, we can say that that now is 0, that inner product. We just have 0 inner product with v, and the 0 vector inner product with any vector is 0. Now we can simply play with some of the properties of our inner product, and in particular, let's look at the additivity of the first slot, or the linearity, but let's say additivity of the first slot now allows us to simply distribute that expression in the first slot into 2 inner products, meaning we now have t dagger t applied to v, inner product with v, minus t dagger applied to v, inner product with v. That also needs to equal 0 for all v in our vector space capital V. And now we can just apply the definition of our adjoint, meaning suppose we group these in a particular way and we simply focus on t dagger in the first slot and t in the second term in the first slot, meaning the first inner product by the definition of the adjoint is equal to that expression with that first operator being, or the adjoint of that first operator sliding over to the second slot. Meaning, if we look at this, by the definition of the adjoint, we now have TV, T dagger, well, we need to take the adjoint of that times V. That's the same scalar that's in the top line in the second line with the first term in that expression. Likewise, for the next one, we have T dagger V, and now we simply take the adjoint of T if we want to in the second slot, and all of that is again equal to 0. What happens when we dagger the dagger? That's just T, isn't it? So now this becomes T, so that we have TV, inner product with TV, minus T dagger V, inner product with T dagger V, equaling 0. Or if we wanted to, I could now simply move one of those to the other side, and TV inner product with TV is simply the norm of TV squared and that's equal to the norm of T dagger V squared, and that's true for all V, and that's what we set out to prove for whatever proposition that was, proposition 7.6. Questions on that? That's where we stopped last time, was just stating that proposition. Now we've hopefully convinced ourselves that if we can show that TV's norm is the same as T dagger V's norm, then we can claim that T is normal, if we wanted to show that the operator T was normal in that way. Let's now look at or make the next observation, and that is that the operator given by, let's write it as T dagger T minus T dagger, is self-adjoint. And one way of showing that is to just take the adjoint of that and show that it equals what's in, or what we started with. So if we now take T dagger T minus T dagger, and we take the adjoint of that, now we simply have to recall what happens when we take the adjoint of a product of operators. So that now we have T dagger T dagger minus T dagger dagger. And what happens when we take the adjoint of T dagger T? We reorder the product so that now we have the dagger of T first, and then we have T dagger daggered. So that now we have T daggered and we have T dagger dagger. If we do the same thing on the second term, we have the adjoint of T with its adjoint, and then we have T with its adjoint. And if we recall that the adjoint of the adjoint is just the original operator, we now have T dagger T minus T dagger, and that's actually what we started with prior to taking the adjoint. And so now we have the adjoint equal to itself, and that's what we needed to show. That T dagger T minus T dagger viewed as an operator is self-adjoint. Let's now look at some properties of T, this operator, being normal. And we'll look at two properties as indicated in our beginning list of goals. If we look at first, let's look at the eigenvalues and the eigenvectors of this normal operator T and its adjoint. And then we will look at what happens when we have distinct eigenvalues of a normal operator T, and we'll see that that actually implies that the eigenvectors are orthogonal. Those are the properties we want to look at, and the first one is stated as a corollary, corollary 7.7, and that says that if we're given an operator t, a linear operator t, that's normal. Remind me again what that means. When an operator is normal, what's another way of saying that? It commutes with its adjoint. So now we know that t dagger is equal to t dagger t when I make this claim. Or given t, then t commutes with its adjoint. If the vector v belongs to the vector space V, is an eigenvector of t, and let's now associate with that vector V the eigenvalue lambda that's in our field of numbers, F, either R or C, then the eigenvector V is also an eigenvector of the adjoint of t, or t dagger, with eigenvalue equal to the conjugate of the original eigenvalue. So if the eigenvalue is real, it's going to equal what we started with. All right. So now what we want to do, actually, before we get too deep into the proof, we're actually going to sort of go aside and look at a lemma. But let's start the proof, and then we'll quickly take sort of a detour via a lemma. First, let's take v and lambda as we were stating in the corollary. Take v and lambda to be, or as eigenvalues and eigenvectors, or as eigenvector of the operator t. That means that we can state that t minus lambda I v is equal to 0. If lambda is an eigenvalue and v is an eigenvector, then we know that t satisfies this relationship, that the eigenvector is in the null space of t minus lambda I as an operator. Now let's look at this t minus lambda I, some properties of that in the form of a lemma. So before we continue, I told you we were just going to barely get started, and then we're going to take a detour. So aside, the following lemma is useful in completing the proof. So what we were trying to do was show this relationship between t and its adjoint and the eigenvectors and the eigenvalues. Before we get too far into that, let's now look at the following lemma, which is a property of this operator t minus lambda I. And the lemma says that if we have a normal operator t, if t is normal, then so is t minus lambda I as an operator. Then t minus lambda I is also normal. And having that t minus lambda I normal, will be nice in the proof of Corollary 7.7. So let's show that if we start with t being normal, which was one of the given assumptions or the hypothesis in the Corollary 7.7, we were assuming that t was normal. Now what we want to be able to do is conclude that we can also say that t minus lambda I is normal. Let's show that by proving this lemma. To prove this lemma, all I'm going to do is really show that t minus lambda I times t minus lambda I dagger is the same as t dagger of, or the dagger times itself. So t minus lambda I dagger t minus lambda I. Or what we're saying is that t minus lambda I is normal or commutes with its adjoint. So t minus lambda I commutes with its adjoint. We have the left-hand side and the right-hand side. Let's just find an expression for the left-hand side and show that we can get the same expression for the right-hand side, and then we'll be able to conclude that those two are equal. Right now, they may not look like they're completely equal. So let's now look at the left-hand side of that equality. We have t minus lambda I times t minus lambda I dagger. I'll do the hard part. T minus lambda I. Now, what happens when we take the adjoint of t minus lambda I as an expression? It's just a plus b, essentially. We can take the adjoint of the two pieces, meaning the first piece is pretty easy. We just take the adjoint of t. And what happens when we take the adjoint of the identity operator? Except now we have to remember we're scaling it by a potentially complex number. We just have to conjugate the scalar. The identity operator's adjoint is just the identity operator. So this now becomes minus lambda star for the adjoint, or I'm sorry, for the conjugate times I, where you could have written this as the adjoint if we wanted, but it's equal to itself as the identity operator. Let's now just perform the multiplication. We now have t dagger, minus lambda I t dagger. It doesn't really matter which way we do it, but I guess I'm multiplying by both terms on the left first, times t dagger. Then we have minus t lambda star I plus, since we have the product of two negatives, lambda star I. Or that's now t dagger minus lambda t dagger minus lambda star. That's a scalar, so it can slide through the operator t. And what's lambda times its conjugate? Not quite. It does sort of fall apart. It does collapse. I shouldn't say falls apart. It collapses. If we have alpha plus j beta times alpha minus j beta, we get alpha squared plus beta squared, which is the magnitude, isn't it? Squared. So this now becomes the magnitude of lambda squared times I. Is that okay? That's now what we've shown the left-hand side to equal. Let's look at the right-hand side. And I've just collapsed the right-hand side. There's the right-hand side. T minus lambda I dagger times T minus lambda I. We now have T minus lambda I dagger times t minus lambda I. Again, we can push that dagger through the sum of the two pieces. We now have t dagger minus the conjugate of lambda times I times t minus lambda I. So that now we have t dagger t minus lambda star I t minus t dagger lambda I plus lambda star lambda times I. And that's now equal to t what in the world am I doing? Oh, what was t? It was normal, wasn't it? So now we have t dagger t, that's equal to its, or how do I want to say this? T commutes with t dagger, so now t dagger t becomes t dagger. Is that okay? Then I have minus, and I could pull that, well, I'll just keep them in the same order as what we have. Minus lambda star t minus lambda t dagger plus the norm of lambda squared I. And that should be the same expression, maybe with a couple of inner pieces interchanged in terms of the sum, but I think that's exactly what we had on the left-hand side. And all we needed to know was that t was normal, or that t commuted with its adjoint to get that. So that now, if t is normal and lambda is an eigenvalue of t, then we know that t minus lambda I is normal. And that now allows us to continue with our proof. So now let me say that we have finished up our aside, and we are now ready to go back to the proof of Corollary 7.7. So now we can say that t minus lambda I is normal. From the above lemma. And if we know that some operator is normal from an earlier corollary, which wasn't too early, or actually from a proposition, proposition 7.6, what did we know about the norm of that operator? Or the norm of that operator applied to a vector? If I have that, and I know that the operator t minus lambda I is normal, what is that also equal to? By proposition 7.6, I can take the adjoint of that operator, t minus lambda I, and it multiplied by v is going to have the same norm as t minus lambda IV. That was proposition 7.6. I now can say that t minus lambda I adjoint v is the same norm. My daggers are looking more and more like plus signs, aren't they? But hopefully you can do your typography a little better than I'm doing mine. Now let's move that dagger through those two operations. This is now equal to t dagger minus lambda star IV. But what do we know about T minus lambda IV? That was coming to us from the eigenvalue-eigenvector relationship, and that was equal to 0. So if that's 0, the 0 vector, then we know its norm is 0. Meaning we can now say that this particular we showed that this was equal to 0, or we started with this being equal to 0. Now we've shown it's equal to T dagger minus lambda star IV's norm, and that also is equal to 0. And what does that relationship now say? That's true for all, or for V and lambda star. Now we know that that vector is in the null space of T dagger minus lambda star I, which means that that V is an eigenvector, and the eigenvalue is lambda star. We can now conclude that V is an eigenvector of the adjoint of T with an eigenvalue of the complex conjugate of the original eigenvalue. And that was fairly quick to be determined because we then first started with T minus lambda I being normal. With T minus lambda I being normal, then we can start equating these norms. Equating those norms allowed us to show something about this eigenvalue-eigenvector relationship of T and its adjoint. That was Corollary 7.7. If T is normal, and you know its eigenvalues and eigenvectors, then you know the eigenvalues and eigenvectors of the adjoint of T. That's Corollary 7.7. Let's now look at the next piece, which was property B of our list, and that's Corollary 8 in Chapter 7. Again, let's start with a normal linear operator T. And this corollary says the eigenvectors of T corresponding to distinct eigenvalues the eigenvectors are in fact orthogonal. Let's just assume some variables for a couple of distinct eigenvalues. Suppose we take alpha and beta as distinct eigenvalues. And let's associate some eigenvectors with those u and v. So with eigenvectors, u and v respectively. What's TU? If alpha and beta are respectively associated with U and V of eigenvalues and eigenvectors, that relationship, then we know that TU is in the same direction as U with the scaling given by alpha. So this is now alpha U. Likewise, TV is simply beta V. Now let's create a particular expression with including alphas, betas, U's, and V's. And in particular, let's form alpha minus beta. That's just a scalar. And let's scale the inner product of U with V. We can do that. We have two vectors, U and V, and we have two scalars, alpha and beta. Let's now just form this expression. Those scalars we can distribute across that inner product. Inner product of U with V is what? Yeah, we're going to show that that's 0. That's correct. So the inner product of U and V, we better show that that's 0 eventually, but now in general that's just a scalar, isn't it? So this expression is just a scalar. Alpha minus beta is a scalar times a scalar. This is just some scalar. But let's now distribute that alpha and the beta across this. So we have alpha UV. Maybe you're getting impatient. You just say, oh, that's 0. This is now alpha times the inner product of U minus V, or U with V, minus beta U with V. Is that okay? And now let's put alpha in the first slot and beta in the second slot as scalars. So that now we have alpha U V, and we have minus U beta, the conjugate, complex conjugate of beta times V. So now we have beta star V. We know what alpha U is in terms of the operator T. We now know that this must be TU V. And what do we know about beta star times V? That's T dagger V, isn't it? So now we know that this is T dagger V. We started with T being normal. So that now we know that the eigenvalue beta of T is associated with the adjoint of T's conjugate of beta as an eigenvalue. And they share the same eigenvectors. So we're using that information. But now, what do we have here? Now I'm ready for your answer. This is TU inner product with V minus U inner product with T dagger V. The right-hand side is really just sliding that linear operator to the second slot, isn't it? Creating the adjoint. Or we could slide, so if we looked at the first term and slid that T from the first slot into the second slot, the first term is the inner product of U with T dagger V. And now we're subtracting U inner product with T dagger V. That expression, or those two terms, are equal to 0 by the definition of the adjoint. And really the adjoint is created so that we can move that operator among the slots. That's the whole, or that's one way of thinking about the adjoint. Now what have we said? Well, we ended up with 0, which I guess everybody supposedly knew when we started. But now we can go back to the very beginning and say whatever we started with on the left, that's now equal to 0. Now we can conclude alpha minus beta times the inner product of u with v is equal to 0. But what do we know about this scalar alpha minus beta? Whoops, I went too far. Alpha and beta were distinct, weren't they? So we now know if we take the difference of two scalars that are distinct, that's not equal to 0, is it? If alpha and beta are distinct. We can now divide by that non-zero number in that expression and end up with what you were wanting me to conclude all along, which was that the inner product of u with v was equal to 0. And this now tells us that by the definition of orthogonality, these vectors are orthogonal. So this is the definition of vectors being orthogonal. What did we just conclude or show? We showed that if we start with a normal operator, if we have distinct eigenvalues of that normal operator, then the eigenvectors associated with those distinct eigenvalues are orthogonal to each other. And that gives us quite a bit of power if we now think about how to start adding up pieces or parts, especially when we get into infinite dimensions. If we have normal operators, then we can say, oh, what's an eigenvalue? Oh, that eigenvalue is distinct from this one. Then we know something about their eigenvectors. They're orthogonal, and that makes it nice when we're starting to combine things or add things up. Think Fourier series in the infinite dimensional case. Let's now get into something else that's nice that maybe you won't think so while we're going through it, but it provides us with some nice results, and that is the spectral theorem. We now come to the end of our journey or quest to find nice basis for these vector spaces. And one of the things that we maybe like in terms of operators is to have diagonal matrix representations of these operators. So remember the appeal of diagonal matrix representations. What's so appealing about that? We basically have decoupled all of our properties to now dealing with scalars, essentially, scalar problems or scalar results. Also, remember also, that an operator only has a diagonal representation and now think of exam number 2. If there exists a basis consisting of eigenvectors of the operator. Now, in addition to this basis, we also want to add something about their length, and we want those to be of unit length, those basis vectors. We want orthonormal basis, so we're now working on an inner product space. We have a norm. So we'll add a further constraint that we like an orthonormal basis. Or we must be in an inner product space. And the spectral theorem actually tells us which operators have eigenvectors that can produce these orthonormal bases. And therefore, which operators have a nice diagonal representation. Fortunately or unfortunately, it really depends on the underlying vector space that we're playing with, and so we're going to separate those two out. We'll look at the spectral theorem for complex vector spaces and the spectral theorem for real vector spaces. The answer that we're working towards depends on whether we're dealing with a real or complex inner product space. So we'll treat the two cases separately. And the easier case we'll treat first, which is the complex case that has less restrictions or constraints. Here's the complex spectral theorem 7.9. V is a CIPS, complex inner product space, and we have a linear operator T on that complex inner product space. This complex inner product space V has an orthonormal basis made up of or consisting of eigenvectors of the linear operator T if and only if T is normal. If T commutes with its adjoint, then we can find an orthonormal basis for our complex inner product space V. That's what this complex spectral theorem is saying. And that basis, those orthonormal basis vectors, are simply the eigenvectors of this linear operator T. This is an if and only if, and which means we can say A implies B and B implies A. We can show both directions and then we're done. For the first half of the proof, let's assume that we're starting with an orthonormal basis. So assume V has an orthonormal basis of eigenvectors of T. Orthonormal now means we're dealing with an inner product space, since we can start normalizing these vectors. What we want to show then that T, well, assume V has an orthonormal basis of eigenvectors of T. Now what we want, or we can now say then that T has a diagonal matrix representation with respect to that basis. T then has a diagonal matrix representation with respect to this basis. How is the matrix representation of the adjoint related to the matrix representation of the operator T? It's the conjugate transpose, isn't it? So the matrix representation of the adjoint of T is the conjugate transpose of the matrix representation of the linear operator T. Then what does the adjoint of T look like? If T has a diagonal matrix representation and M of T dagger is the conjugate transpose, then we know that a diagonal transposed is still diagonal. So T dagger also has a diagonal form with respect to this basis. And now we can just sort of play a little bit with these matrix representations. Meaning, if we consider the product of two diagonal matrices, then we're going to be able to show that these basically commute, and we can now say that these linear operators commute, T with its adjoint. Here's a matrix product. Let's say that we have A1, A2, down to A sub n, zeros, it's just a diagonal matrix, zeros on the off diagonal, multiplying B1, B2, another diagonal matrix down to B sub n. What does that look like? So now if we look at the second matrix and we say, okay, what's the first column going to look like in the product of this diagonal times another diagonal? We have B1 scaling the first column, isn't it? And the first column is only A1. So our first column in the product is simply going to be the first column, A1, scaled by B1, but there was nothing below A1. If we do the same thing with B sub 2, B sub 2 is going to scale the second column, and the only non-zero term in the second column is A sub 2, and we just see that we end up with a diagonal matrix with the diagonal entries being the product of those elements on the two diagonals of the original matrices. The observation is just to see that we get the same result if we change the order or interchange the order of those two diagonal matrices. If we now look at B1, B2, B sub n times A1, A2, A sub n, we get the same behavior, don't we? We still get B1, A1, B2, A2, and those scalars commute, whoops, and A could be the matrix representation of T, B could be the matrix representation of T dagger. We've now shown that their matrix representations commute. Therefore, any two diagonal matrices commute. Therefore, the composition of T with its adjoint is the same as T dagger times T, or composed with T. Or T and its adjoint commute. And another way of saying that is to conclude that T is normal, and that's what we wanted to show. That was the one direction. Now if we go in the other direction and start with this operator being normal, then we have to show that we end up with diagonal matrix representations for T and T dagger. This one's maybe not as easy to see, but now let's assume T. Maybe I shouldn't have even said that, huh? Maybe I just should have said 0 and move on. T is normal. That's the assumption that we're making. If T is normal, what do we know about T even if it wasn't normal? If it's in a complex inner product space or just in a complex vector space, what do we know about a linear operator? It can be upper triangularized, can't it? So T has an upper triangular representation just from the fact that it lives in this inner product or this complex vector space. That's true for any operator on a complex vector space. And that was, if you need to follow up with that, that was Theorem 13 in Chapter 5, if you want to convince yourself of that fact. Which means the following. If I now wanted to write the matrix representation of T, there's some basis, which since we're on an inner product space, we can normalize that basis. We now have these vectors, E1 through En, that can actually be orthonormal basis vectors, such that we have an upper triangular matrix for matrix representation for T. We now have an A11, an A12, an A13, all the way down to A1n, A22, A23, A2n. Everything else below the diagonal is 0. We have an upper triangular matrix representation for this linear map T, where these basis vectors are an orthonormal basis set for some orthonormal basis, E1 through En. Now, if we start with that matrix representation, if we now take the first basis vector, E1, and apply to that the matrix representation of this linear map, we now have A11, A12, A1n, A22, down to A sub nn. E1 is the first orthonormal basis. That, in fact, is going to be, for this particular, we know that we have eigenvalues on the diagonal, and this orthonormal basis is going to now, basically, we need to have this satisfy some eigenvalue-eigenvector relationship. E1 is normalized, orthonormal, so it has a length of 1. It has to have just a 1 in the top coordinate, so that when multiplied on the right by, or multiplying this matrix representation on the right by this E1 gives us this eigenvalue-eigenvector relationship, which is lambda E1, and lambda is the element on the diagonal of this upper diagonal, which is A11, meaning this is now A11 which is this lambda E1. And we're just going to call it this A1 scaling the first component, and it's 0 everywhere else. Or you could think of this now as saying that E1 is an eigenvector, or it's invariant with respect to this linear map T. If we know that this TE1 gives rise to this vector on the right, and I said, well, what's the norm squared of TE1? That needs to equal the, well, TE1 is just this right-hand column. What's the norm squared of that column vector? The norm of A11 squared. We just have one scalar scaling this vector, and so the only non-zero entry in there is that element. So this is now A11 squared. That's the norm of TE1 squared. Now, we also know something about the matrix representation of the adjoint. Similarly, we can consider the matrix representation of the adjoint of T. And we said that that's the complex conjugate transpose of the matrix representation of T. So this matrix representation of the adjoint of T, as we can consider it as the conjugate transpose of M of T and conclude that now the norm of T dagger E1 squared, they share the same eigenvectors, but now the matrix representation of T dagger is the conjugate transpose of the matrix representation of T, which now says that the result of the matrix representation of T dagger times E1 is going to be a column vector made up of what? If I transpose, let's just transpose this, forget about complex conjugate, and now that first row becomes the first column. We operate on that with E1, where E1 was just 1, 0, 0. That just pulls off the first column. We now simply have that first row in the first column. And if we take the norm squared of that column, we now do have the sum of each of those elements absolute values squared. We now can say that the norm squared of T adjoint E1 is now equal to, A11 squared plus A12 squared plus A sub 1n squared. Now we have to go back to the very first statement in this line of the proof. T we assumed is normal. If T is normal, there's now a relationship between the norm of T in a vector and T adjoint in its vector. But T is normal from proposition 6 in chapter 7 we know that TV square norm is equal to T dagger V norm. If we now take, and that was true for any V, if we now take V to actually be E1, now we can see that this implies that this norm for TE1 squared must equal the norm of T dagger E1 squared, or the absolute value of A11 squared equals this sum of absolute values. This implies then that A11 squared is equal to A11 squared plus A12 squared plus A1n squared. If the left-hand side is equal to the right-hand side, I can see two entries that are the same, and the others shouldn't be there. If they shouldn't be there, then we're basically saying that all of these off-diagonal terms are 0. And that now says the matrix representation of T, the first row needed to just have one element in it, which was the first element, and the column was already zeroed out because it was upper triangular. So the matrix representation of T must really look like A11 0, A1 or A22, A23, A2n, A33, A3n, all the way down to ANN, and that's 0. But now can you see we can just continue this process? Meaning we showed it for the top row. Now let's just do the same thing for the second row. And we're going to conclude that all those off diagonal terms in the second row must be 0. Because we can find E2. And E2, scaling that, has to be the same. Basically, we've now concluded that with T normal, its matrix representation is diagonal. So that now, let me just say, but, wow. We can repeat this process for E2, E3, down to E sub n. I'll skip some details and say that the matrix representation of T is now diagonal. Therefore, the eigenvectors of T do form an orthonormal basis. And that then, with those extra pieces filled in of doing that again, shows that now we've shown the complex spectral theorem. We'll pick up at that point on Wednesday with the real spectral theorem, and that takes a little bit more doing.